So the basic element type of two-dimensional problem, we may select the triangular element like this. And if we define the node, we have 3 nodes, right? And for each node has 2 degree freedom, that is the displacement in x direction and displacement in y direction. If we have two direction of displacement for each node, it means that for this type of element, it composed of 6 degree of freedom. Okay, 2 degree of freedom per node. Okay, and for this, we define the node I, node J, and node M. Okay, we define node, the name of the node to be IJM. Actually, IJM is maybe the switch to is up to us that to define. Okay, but one thing that we have to concern is in order to define the name of the node, is have to follow this rule. The node IJM that we apply has to be consistency in direction for every element. Okay, so then for this course, okay, and from this textbook, and actually is for the general one, for the general case of the finite element, we define the node IJM by this sequence. It has to counterclockwise sequence. It has to, the number should be in counterclockwise sequence. So that means if this triangular shape, okay, if you define the node this as node I, so then what it should be node J. This should be node J, and this should be node M. Okay, it should be in counterclockwise direction. Okay, it's very important because when we use in opposite direction, you will obtain the different side of the signet. That is not this. We have to follow the rule. This rule. Okay, and also if we change, it should be I. So then it should be J and it should be M. Okay, IJM is the local node, local name of the node. For the global one, this may be not in this sequence. It may be node I is maybe node number 10, for example. Node J is maybe node number 4. Node M is maybe node number 6 or something. Okay, it's up to the problem. Okay, so then when we derive the element signet, we have to consider the global node number and fit it to the local one, that is IJM. That's what we will define to be I, and what if we define this node to be I, then another one has to be in sequence. For example, if we select node number 4 to be I, so then for this element, node J should be 6, okay, and node M should be 10. All right, okay, for that. This is very important. And then for this case, we already select type of the element already, and then okay, as I mentioned above, we the directions of the IJM is in counterclockwise, and the degree of freedom is related to IJM for the local one. Okay, UI VI, UJ VJ, and UM VF. We select the displacement function, okay, to be the linear displacement. So then we call this type, okay, in finite element software, it may call this the linear type of element. Okay, it means that we use the linear shape function, we use the linear interpolation function of the displacement. We approximate displacement in size of the element. We approximate displacement in size of the element. It's maybe in this point P. Okay, that is depend on the coordinate of this point x, y. Okay. We define it like the linear function like this. Okay. And after that, it means that when we would like to find ui, this at node, ui, uj, okay, and um and vi, vj, vm is depend on the coordinate of any point. And these are this point, this maybe I, and this j, and this m. So at point I, you have the coordinate xi, yi, okay, and this you have coordinate xj, yj, right? Okay, and also xm, ym. Okay, according to this, so then we follow the step. We can solve for the shape function by using this, and we would like to find a1, a2, and a3. We have to find this inverse metric. Okay, and this inverse metric is right in this form. Okay, you may derive it by yourself, but for this case, it's derived by this. Okay, you see that you have the 2a. A actually is the area. The area of the element. Okay, but the area of the element, if you know the coordinate, if you know the coordinate of the point, for example, actually the area of the triangle, we can determine is very easy for the case of right angle, right? If you have the right angle shape, okay, area is a half BH. This is very easy to determine. Okay, for that case that you know the dimension of the side of each side of the triangular shape, we can find the area directly. But for this case, you may not know the length of each side directly, but you know the coordinate of each point in stage. For example, you know xi, yi, and you know xj, yj, okay, and you know xm, ym. Okay, you know the coordinate in stage. For this case, if you know the coordinate, you can find the area by determined by the determinant of 1 xi, yi, 1 xj, yj, and 1 xm, yn. The determinant of this matrix is equal to 2a, and after that you can find the area by divided by 2. Okay, this is the from the mathematics. Okay, so then we have the area equal to this, and x and alpha, beta, and gamma, alpha I, beta, alpha, beta, and gamma, alpha I, alpha j, alpha m, beta I, beta j, and beta m, and also gamma I, gamma j, and gamma m is defined by using the coordinate of each node by this. Okay, so according to this term, we can find a1, a2, and a3 by this. Okay, and also a4, a5, a6 determined in the same manner that is related to vi, vj, and vm instead. According to this, when we rearrange the term and substitute the rearrange and with some manipulation, we have the shape function. This is the shape function of the triangular shape, constant strain triangular shape. Okay, the shape function defined by ni, nj, and nm by this term alpha I, beta I, and gamma I, like this alpha j, beta j, gamma j. Okay, What does it mean? It means that if we know the displacement at node, same as the one-dimensional case, if we know the displacement at node, we can determine the displacement inside of the element. Okay, we have the element. This is node I, this is node J, this is node M. After we proceed the finite element procedure, we obtain the displacement at node, right? That is UI VJ. UI VI. UI VI and UJ VJ and UM VM. That is the solution that we, after we proceed the finite element procedure, we obtain the displacement at node. But if we would like to find the displacement inside of the element, how can we do? We use the shape function. Okay, we apply shape function to solve it. Okay, and then we obtain, we can determine the displacement inside of the element as point P. Okay, and from these two equations, we can rearrange the equation into the metric form like this. So then the vector sign actually this represent the displacement inside of the element. Okay, defined by ND, that is the shape function metric is defined by this. Okay, and then now we already know the shape function. Okay, then we will derive the element stiffness. Okay, we define the strain displacement relation. We define the strain displacement relation according to theory of elasticity that we have learned before. Okay, for small displacement case, we found that epsilon x, epsilon y, and gamma xy is divided by this. Okay, divided by this. So then epsilon x, that is partial u by partial x, is equal to the first derivative of u with respect to x. What does it mean? It means that for u is equal to nd, right? So then we take the first derivative of displacement with respect to x, then we have this term. So then ux is equal to the first derivative of the shape function ni, nj, and nm with respect to x. Okay. And also for this case, when we take the first derivative to this, we obtain ni, the first derivative of ni with respect to x equal to beta I over 2a. Okay, and similarly with nj and nm, we have beta j over 2a and beta m over 2a. Okay, in the same manner for another case, okay, we can derive, after we derive this each term and then we rearrange the term, we obtain the strain. This is the strain vector that is equal to epsilon x, epsilon y, and also gamma xy related to the displacement at node, that is come from 6 components. Okay, it's related with the constant metric over here that is composed of beta I, beta j, beta m, gamma I, gamma j, gamma m, composed of this term. Okay, we can write this in the metric form like this. It's just a simplified term. But actually, if you are confused about this, you can remember this equation instead. But this equation is right, actually is right in the submetric form for the submetric. Bi is defined by this submetric. Bj is defined by this submetric. Actually, if you compare equation 31 and 30, okay, it is the same. So then we have the epsilon equal to BD like this. And we consider the stress-strain relationship. For stress-strain relationship, for the case of plane problem, you have to remind yourself that metric D is depend on it is the plane stress or the plane strain. You have to select the correct one. Okay, because we simplify the three-dimensional problem to be the two-dimensional problem. So then metric D is necessary to select the correct one. Is it a plane stress or plane strain? Okay, but when it's rearranged, it's right in the same equation, that is sigma equal to B BD. Okay, D, the capital D metric represent the material metric that is up to the problem. If it is plane stress, it's defined by the plane stress problem. If it is plane strain, you have to select the correct metric D for plane strain problem. Okay, but for metric B and nodal displacement is the same. Okay, it is the same. After that, we derive the element stiffness metric by applying the stationary principle of minimum potential energy. We apply principle of minimum potential energy, that is energy method. We formulate the equation by consider the strain energy of the element and the potential energy due to the external force. Okay, the strain energy of the system is composed of the strain and stress related to each other in order to derive the strain energy. Okay, according to this equation, okay, and the potential energy due to the force, the applied force, that for this case is composed of body force, okay, and concentrate force. For the concentrate force, it is equal to D transpose P. Okay, for the potential energy is equal to the negative value of the work done. And also for the surface load, that is actually is for the case of distributed load also. After we derive the term for each term and substitute each term in term of finite element like this, and after that we take the first derivative. Okay, we rearrange this term. Okay, you see that it is the indicated by volume, right? Okay, but if we consider the thickness is the uniform thickness, it will reduce from indicated by volume to be indicated by over the area instead. And after that, when we rearrange this term and we consider on the right hand side and some manipulation, we have the potential energy right in this form. Okay, and the metric, the vector F represent the applied force that is composed of the body force, concentrate force, and the surface force. Okay, after that we apply the principle of minimum potential energy. Okay, we take the derivative of this equation with respect to the nodal displacement for each, and then we obtain this equation and we define this term. We define this term as the stiffness metric K. Okay, then for the constant strain triangle, we can derive the element stiffness by integrate this term, that is integrated by the volume. Okay, but for the general case that the element with the constant thickness T that we mentioned too, for the case that the thickness is constant, so then we reduce the integral term by volume to be the integral term by area instead. And if we consider metric B from previous step, we will see that metric B actually is the constant. It is not in terms of x and y anymore. So then this integration term over area is very easy because we can rearrange it to be this. Because metric B is constant, metric D is also constant, and metric B is constant. So then it's become integrate of dx dy. So then it's become the area. Okay. So then the constant strain triangle stiffness is defined by metric K equal to T, that is the thickness, multiplied with area, and multiplied with the metric B transpose D and metric B. Okay, that's we after we solve this. What is this? Metric B is the size of 3 by 6. Okay, transpose becomes 6 by 3, and metric B is 3 by 3. So then element stiffness is composed of 6 by 6 is the size of the element stiffness for the constant strain triangle. It's become 6 by 6. Okay, that we can write in the submetric form like this, but actually it's not necessary to do like that. Okay, so then we will derive if we have the element stiffness already, that is right in terms of K11, K12, and so on. Okay, we have 6 by 6 component. Okay, related with the force and the displacement is known. Okay, displacement is known is U1, V1, U2, V2, and U3, VT, like this. Okay, after that we proceed the same procedure that we familiar with for the general one. We assemble it together and we can solve. Okay, so this is a transformation metric. And then after we have the nodal displacement, we can solve for the element force and the nodal force also. Okay, I think it should be enough for today. And